Hello! Today we are going to talk about how we simplify basic radical expressions. Last time we've met, we talked about simplifying expressions like square root of 49. We said that 49 could be rewritten as 7 squared, and when you still leave it under the radical, like we're supposed to, square root will cancel out the square of 7, simply because square of a number and taking the square root of a number are two opposite operations. That explains why square root of 49 equals 7. We also talked about a general situation. A number x to the second power is taken a square root of. We said that these two operations will cancel each other and the result would be x. This simple property will allow us to simplify expressions that are slightly more interesting. Observe a square root of 49 and tell me how it's different from square root of 32. Correct. The difference between these two expressions is that square root of 32 does not have a perfect square number openly written. It's hidden somewhere within the 32. So the first thing we're going to do is we will look for the biggest possible perfect square number that divides into 32 without a remainder. So I will generate a list of perfect square numbers. Here it is. Perfect square numbers all the way to 196, and we will not need anything more than that. On your calculator, I will ask you to dial the radicand itself, 32. At the same time, we're going to identify where in this list 32 would lie. It would lie somewhere between 25 and 36. This is why we need it. We will dial 32 in your calculator and divide by the first perfect square number, that is just under the 32. You see that the result is not a round number, so 32 is not divisible by 25. We will continue this process till we find the greatest perfect square number by which 32 is divisible. So the next number in line is 16. But 32 divided by 16 perfectly produced number 2. That will allow us to rewrite a square root of 32 as a product of greatest possible perfect square number, 16, and number 2. Now we will recall that when we have a product under the radical, we can rewrite it as a product of two radicals. Now we will tackle every one of these radicals separately. We are going to say that square root of 16 is the same as 4 to the second power, and we will remember to take a square root of it. These two operations will cancel each other. The result would be 4. But it's also multiplied by a square root of 2, which we cannot simplify any further. Therefore, it's our final result. Now, some of you might wonder, why is it that we had to introduce 32 as a product of 16 and 2? What if somebody had a slightly different approach? What if you dial the 32 as a product of 4 and 8? Let's see what will happen then, because whether or not your answer is correct really depends on what you do with your solution. We will break this product into a radical 4 times radical 8. We now simply can see that square root of 4 could be introduced as a square root of 2 to the second power. we will now cancel the square root and second power of 2, which will leave us with 2 square roots of 8. If you stopped right here, then your answer is not complete. Why is that? Well, think about the radicand of 8. It is still divisible by one of the perfect square numbers. It is divisible by 4. And that is exactly why this result is not considered to be in simplest radical form. So you must be savvy enough to understand that, recognize it, and continue simplifying square root of 8. It's going to be 2 multiplied by square root of 4 divided by 2, because now you're introducing the 8 as a product of the biggest perfect square number and the 2. Then you will continue with preserving your 2 and breaking this product into radical 4 times square root of 2. Now, this is our perfect square number. As we take a square root of it, we will use a notation 2 to the second power. So I'm going to copy the 2. I'm going to write 4 as 2 to the second and take a square root of it. And this radical of 2 is not going to be changing. Again, we're canceling square root and second power of number, which leaves us with this 2. This becomes a 2, and it's still multiplied by square root of 2. Now we want to simplify these two coefficients. 2 times 2 becomes a 4. Now our result is the same as in the previous process. Under the radical we have 2, and clearly it is not divisible by any perfect square numbers. That is how we know that this result now is in simplest radical form. So the bottom line of this example is, it is very important that in the very beginning you break your radicand into a product of the greatest possible perfect square number. Not just any perfect square number like in our second situation. The reason for that is that we don't want to be stuck with a half-done answer. Anyway, it's always a good practice at the end, when you think that you are done and you have a final answer, look at your radicand and ask yourself, maybe it still could be divisible by greatest perfect square number or any perfect square number. In that case, you will need to simplify further. Now, it's always a good idea to double check your example if this is what we had originally and this is our answer. You want to dial them both in the calculator and see if they produce the same result. Square root of 32 equals 5 and about 7, as 4 square roots of 2 produce exactly the same answer. Now, keep in mind, the answer that would not be a final result also would produce the same integer value. That is why it is very important to be vigilant when you think you found your final answer and check the radicand on divisibility by perfect square numbers. Right now, I would like you to pause your video and copy the steps of simplifying radical expressions in your notebook. Step number 1 is always generate the list of perfect square numbers, just like I did. Step number 2, break the radicand into a product composed of largest perfect square number and a number that completes it by multiplication. Step number 3, you break one radical sign into two radical signs. We use the rule that you could see on the screen. It simply states that if you have a radical of the product, then you can rewrite it as a product of radicals. And once you've done that, the last step will require you to simplify the perfect square number and leave the number that's not a perfect square the way it is. Here is an example of simplifying expressions such as square root of 20. Please keep the process that you just copied in your notebook and refer to it every step of the way. Step number 1 is always generate perfect square number row. Square root of 20 means that you will work with a radicand. So you will take number 20 in the calculator and you will break it by division using a perfect square number who is just under the 20. The 20 would be somewhere here. So you will be breaking it by 16. You will quickly find out that 20 is not divisible by 16. So you will continue the process with the 9. 20 is not divisible by the 9. You must see it on the screen of your calculator. The next number that's left is 4. You will find that 20 could be rewritten as a square root of 4 multiplied by 5. Next step is rewriting a square root as 2 square roots multiplied. Now, square root of 4 could be rewritten as a square root of 2 to the second power, which means that you now can cancel square root and a second power, as a result of which you receive 2. 2 square roots of 5 is the answer here. Move on with the next example. Do you agree or disagree with the following question? You should disagree, because the student broke 20 into a product of 2 and 4. That really doesn't help us because neither 2 nor 10 is a perfect square number. So we can't really proceed with simplifying it further. This is not a helpful approach. I'd invite you to simplify square root of 54 on your own. You may pause the video. Square root of 54 means that you will be working with 54 radicand, which belongs somewhere around here. So you would divide 54 by 49, 36, 25, 16, 9, until you find the divisor that gives you a round number. So 9 and 6 would be exactly a pair that you're looking for. Now you will break it into 2 radicals, square root of 9 times square root of 6, and rewrite 9 as your perfect square number as a square root of 3 to the second power. Of course, that means that you will be able to cancel square and take in a square root of a number, which means that you have the answer 3 square root of 6. Let's continue with our examples. Square root of 300. Feel free to pause the video and always refer to the process that you outlined earlier in this green box. Again, your first step is generating the perfect square row. 300 will belong somewhere right here. So you will divide 300 by every perfect square number below it until you find the greatest possible number that divides it without a remainder. That would be 100 multiplied by 3. So you'll break it into 2 radicals, one of which is a radical square root of 100. You cannot simplify square root of 3, so you will leave it, and 100 under the square root will be rewritten through 10 to the second power. Again, this means that you are canceling second power and square root since they are opposite operations, and you have square root of 3 multiplied by 10. Since it's more appropriate to write coefficient right in front of variable, we will rewrite this answer as 10 square roots of 3. Please continue on your own with the example D. Notice that radical of 20 is multiplied by 2. That simply means that 2 would be carried over until you finish simplifying radical of 20. So you see I carried the 2, and then I broke 20, just like in the previous example, into the highest perfect square number that is divisible by 4 and 5. Then I continued with breaking the one radical sign into two radical signs. I followed up with copying the 2 and rewriting square root of 4 as a square of 2, so that I can apply the property that we mentioned earlier several times. That will mean that I already have 2. A new 2 is formed from this part of the expression, and it's still multiplied by square root of 5. So we can simplify these two coefficients, saying that the final answer is 4 square root of 5. And that is the end.